Alrighty, welcome back to good old operating systems. So today, fairly chill lecture. Hopefully we can be over with it fast, get back to lab questions if anyone has any lab questions. Hopefully you've started the lab, otherwise yikes. Yeah?
You said that this won't be on the midterm, but it'll be on the exam?
No, so this won't be tested at all for anything. This is just for you because if you have ever used the internet before or a web browser or want to communicate using the network, it's what sockets is. So it ties into this course because it doesn't really add anything that more, and then what we get out of it is, yay, we can communicate across the network and across computers, which is really fun. So let's just dive into it. So sockets are just another form of inter-process communication. So far we've seen pipes, we've seen signals, we've seen shared memory even. But these forms of IPC, well, they can only communicate between processes that are on the same machine. What if we want to communicate between different machines? And that's where sockets come into play. So sockets enabled inter-process communication between physical machines, and typically this will be done over a network. So whenever you visit any web page on the planet, you're using sockets. So there are there are two kinds of sockets. There are sockets that are supposed to represent a server. Like if you go to google.com, you connect to a server that supplies your web browser some information, and then you render that, and then you can see google.com. So the server side is the more complicated side. So there are 4 steps if you want to use a socket for as a server. And they are, first, there is a system call called socket that will create a socket. And spoiler alert, it just gives you a file descriptor. So that file descriptor represents a socket, and then everything you know about file descriptors is the exact same. You can read and write to it or do whatever you want. The other steps are a bit weird. So there is the second step, which is bind, which means we attach the socket to some location. So that could be a file, which we'll see in the example today, or an IP address with a port, so on and so forth, some way to actually form a connection with this server through some known name. The third one is a listen step, and that indicates you will accept connections. So you are going to accept connections, and basically the kernel will take care of queuing all the connections for you. If like 1 million people try and connect or something like that, it has an internal queue, and you can set a queue limit. Then for the 4th step and the final step, you do an accept system call, and that will return the next incoming connection for you to handle, and it will also be a file descriptor. So whatever file descriptor you get from accept represents a connection between you and another person or another program, and you can read and write information to them, and it goes across the network. So clients have a much simpler job. They only use 1 socket per connection, so you create a socket with the same socket system call, and then you use a connect system call. So that connects to some location, and now the socket is active. It can now send and receive data, and the file descriptor from the server end that got returned from accept can communicate using that same file descriptor. The information just goes the other way. So this is what the socket system call looks like. It takes 3 arguments, a domain, a type, and a protocol. The domain is kind of just the general protocol to use. It's further specified by that 3rd protocol argument, which typically no one ever uses anymore. So basically, the domain actually represents the protocol. So there's 3 main ones you'll see. There's AF Unix, which is for local communication, which is on the same physical machine, and generally the name for that is just a file name. The other ones are INET, so that's IPv4, so like 8.8.8.8. If you've heard of an address like that before, that's an IPv4 address. And then IPv6, because we ran out of IP addresses, so that's that naming scheme, which has colons and hex characters, and it's lots of fun. So the type is usually one of two options, stream or datagram sockets. If you have ever heard the term, has anyone ever heard the term TCP or UDP before? Yeah, we got a few of those. So yeah, network, which, have you taken the network course? Oh, okay, then this will be easy. This is, have you actually used sockets then?
Yeah, we have a lab in using sockets.
Oh, well, there you go. So the sockets should actually be taught here, but here we go. So stream sockets are like TCP connections, datagram sockets are like UDP, and we'll go into that in a little bit. So, like I said, stream sockets use TCP. That means all data sent by the client appears in the same order in the server, and so on and so forth. And you form a persistent connection between them. As soon as that connection gets interrupted because someone pulls a network cable or something like that, you are notified of it and it says lost connection or something like that. So this is reliable, but may be slow, and especially when you get into the networking course, you'll realize that, hey, things appearing in order given a network isn't always the case. Networks can do weird things. So TCP protocol, make sure everything's ordered. There's going to be some overhead associated with that. Datagram sockets, on the other hand, use UDP, and you just send messages or packets between the client and the server. There's no persistent connection between them. It's really fast because you don't get any acknowledgement or anything like that. But any messages you send to the server could appear in different orders depending on how the packets get routed, or they might not even make it there at all, and you will not know the difference. So generally, you pick TCP because it does a lot of the work for you. If you really get into performance, like where if you send something and they don't get it, it's too late anyways, like a game or something like that, that needs really, really fast response times, you just use UDP because resending it, that time has already passed. The state of the world is different, so why would I bother to send it again? All right, so the bind system call takes a socket file descriptor as the first argument, and then an address. And the address is over two arguments, so there's a struct socket address, which is different depending on what name you're trying to connect to, so there's one for each of the three different types. And then last one is a length because it's C and it doesn't know how long it is, so you have to tell it how long it is. So the three structs that are different is there's sock address, so short for socket address, and then underscore UN. I don't know why they just can't type in Unix, why it has to be UN, but don't ask me. So for local communication, it's just a path that looks like a file. For IN or IPv4, it's an address like 8.8.8, and for IPv6, it's like some ugly hex thing that's separated by colons. Oops. So listen system call sets the queue length and limits for incoming connections. So you just give it that same socket file descriptor and then an integer with the maximum queue length that you want it to maintain. And what it will do is the kernel itself will queue up to that many connections as specified by that backlog argument. And after that, you would just get a connection failed message, and the kernel would just drop the connection whenever someone tries to connect and your queue is full. So if we just set it to default, we let the kernel figure it out, get the default size. Kernel's pretty smart. All right, the last part of the server is the accept system call that blocks until someone tries to connect to it. So again, takes the socket file descriptor as the first argument, and then the address again, and the address length. And these are optional because this could represent like a UDP connection or something like that. So if you already set it in the listen system call, or sorry, the bind system call, then you don't have to worry about these, set them to null and just ignore them. And at the end of this, like I said before, this returns a new file descriptor, and then we can do read and write system calls as before, and now they get sent over the network. So this is the client. The client just has a connect system call that just takes that socket file descriptor and then the address. similar to the bind for the server. So you would have to try and connect to the same thing that the server is listening on. So all of that is exactly the same as bind. And if this call succeeds, it returns you a normal file descriptor that you can read and write. And that's how you communicate with the server. So let us just go into the example, and then we can wrap up quickly and go back to the lab, and I guess your other midterms if you are so inclined. Okay, so here is our main. I will make that slightly bigger. Here's our main. We're going to register some signals like we've seen before. This is just so we can exit properly, so we'll go over what our signal handler does in a little bit. But we're trying to be a server in this code, so we are creating a socket with the Unix file type, so we're not going to try and connect using an IP or anything. We're just going to connect using a file name. And we will say sock stream. That will give us that stream connection, so, or TCP, so everything's in the same order, and we don't have to worry about it. And then the protocol parameter is just unused. So of course, we would do what I have been harping about this entire course. You may have debugged for an extra 10 hours on lab 2 because you didn't listen to me. So here I check for an error, and if there is an error, I exit immediately, so I know of it. So our next step is we want to bind, so we need to set up a string so we can bind to it. So here we create a socket address for that Unix name. This bracket just initializes that whole structure to 0, and then we also have to specify in that structure what the domain is or the protocol. So it should match exactly what you have in the socket system call. And then here I fill in the sun path field, and that is just the name of the socket to connect to. In this case, my path is defined as a define, and it expands to just example.sock. So this should create a file called example.sock, or something that looks like a file, and that represents our socket. Otherwise, I'd say how much of the string to copy. Don't need to copy the null byte or anything like that. Then I bind to that socket address, check for errors, of course. Then I listen. I give it a 0 for that queue depth because I don't care. I'm just going to use the default. Check for errors. And then I have a while true. So if you ever use a web server or host a web server, the core of your web server looks exactly like this. So it's just while true, it does an accept system call. So it's just waiting for connections, waiting for people to connect to it. So this will do an accept system call, which will block until there's a connection, and then it will finally return from the system call. And I just use that socket file descriptor. So whenever it returns, I get a new file descriptor that represents that connection. So because I am a server, I will send the client some information. So here I create a message called hello there. I calculate its length with the null byte, or with the null byte, and then I just do a write system call. So we've all done write system calls, hopefully, and this will send information possibly across a network, but in this case it's just on my machine, but it could be a network depending on what you listen to. So here, check for errors, check that it writes the whole message, otherwise I print off some error messages, and then here I just close that connection, and then the loop would just restart again, and then wait for an accept again, wait for a new client, so on and so forth. So in my register signal, that's the only way I can end this process cleanly. So I created a file called example.sock that represents a socket. So I should close it, but because I'm in an infinite loop, I don't really know when to close it. And the answer to that is, well, I should register a signal, and I should close it successfully in my signal handler. So here, I register my handle signal function, and in here, all I do is call close socket, and in close socket, I close the file descriptor that represents my socket, and then I do this unlink system call, which we haven't seen before. This basically just removes that file so that it doesn't show there before, because if we didn't remove it, it would just be there and now we can't really use it. So let us run this. So if we run it, looks like it's not doing anything, right? Because, well, it doesn't printf or do anything anyways, and if we straced it, we would see that it is blocked on that accept system call because no one has connected to it yet. So we can switch over to our client, and our client would do the same steps, set up the same socket system call, AF Unix sock stream, so it should match what you're connected to, otherwise you'll get an error. And then here I create that socket address. It's a Unix socket. It goes to the same path, so it should be example.sock. And then because I am now a client, I just call connect to it. So I call connect, and then if connect is successful, it doesn't return a new file descriptor. It just makes this file, that socket file descriptor actually usable so I can read and write to it. So in this case, I'm just going to create a buffer and then do a read system call and just keep reading over and over again while I get some data, all the data we can get until we get that end of file character, because we'll get that because the server closes the connection on us, so we know it's not possible to get data. And then at the end of it, I will just printf whatever I received across the socket. So if I go back to a new terminal, I can see that there is this example.sock, so that is what the server is bound to and listening on. And then if I run the client, yay, I received hello world. Or not hello world, hello there, wow, formal. All right, any questions about that? That is a web server. So not too much different, right? If we know one form of IPC, the only difference is how you set it up. But after that, read and write system calls. Now they go over the network. Yay. Any questions? Pretty cool. Awesome stuff. So you will use this in other courses, or if you ever have to do anything involving the web, uses this. And if you want to verify it, go ahead and strace your web browser if you're brave enough. So if you strace your web browser, you'll see that, well, it has to communicate with the system and it connects to the internet, so it has to use sockets. So if no questions or want me to do anything silly with this example, see what would happen.
Since you only sent one message from the server, you can try to build again or to run again, I mean?
Yeah.
Okay.
Yeah, so I can run it again because all the server does is each time we connect to it, this accept would return. We send it a message, and then we just close that file, close that connection, and then we just wait for the next one. So I can run this client as many times as I want, and I get a message from the server. Yep.
How many clients can the server hold like at a time?
So the question is, how many clients can the server hold at a time? So in this, how I wrote this server is I only serve one client at a time right now. So I just accept a connection, I write a message, I close the connection, so I only handle one at a time. And how many clients can try and connect to it at the same time is determined by the queue depth of that listen system call until it starts dropping connections. So if I wanted to, I could write, launch a bunch of shells that launch a bunch of processes that try and connect to it and see when it starts dying, but it's probably a really big number. Yeah.
Could we run the client after closing the server?
Yeah, let's run the client after closing the server then. So if I press Control-C, should shut down normally because I close that socket and I remove that entry. Here I can see that there's no example.sock there. So if I try and use the client now, it says connect, no such file directory, doesn't exist anymore. If I want to, we could start a different one. So let's say I messed up. So let's just say I forgot to do this in the server. So I forgot to unlink, which basically just removes that example.sock entry. So if I go ahead, build this, and run the server, and then close the server. So the server's not running, but that file is still there. So if I try and run the client again, I shouldn't get no such file directory because it's clearly there. So let's see what happens. Connection refused. So there's nothing's listening to it. It's just a socket floating off in somewhere. I don't know, pick your favorite place. So this is why it's always good to check for error messages too. And connection refused, who has seen that whenever they try and connect to a website? Yeah, guess what? It's this. All right, any other questions? I think that's the most we can break it without writing another script that like tries to see the maximum number of clients I can send to it. But because it's on my machine, it's probably really big. Yeah.
Is this like the most common form of IPC, I guess?
Yeah, question, is this the most common form of IPC?
Why would someone want to use pipes when they can do this, I guess?
Yeah, why would someone ever want to use pipes when they can do this? So pipes are a bit more private because you share them directly with your children and you know anything that is unrelated cannot connect to it and cannot get access to your pipe. While in this, if I know the file name and I have permissions to get to it, any process could connect to that, right? Which sometimes you might not want. So that's about the only thing that's different. But this is a lot easier. Typically, you write programs that want to communicate with anything, and then in that case, you just use a socket because you want to throw it on the internet or something like that. All right, any other questions? Cool, let's just polish off the slides. So instead of read or write, there's also system calls that essentially do the same thing, except they have some special flags. So like there's a send and receive system call that do network specific things, which you will not understand what these things actually are until you take a networking course. So there's like out of band data, which is really weird. There's peek, so you can look at data without actually reading it. So you just take a peek at it, and then you can forward it to somewhere else in your program that actually reads all of the data. Then there's this don't route flag, which sounds really weird. So that sends the data without routing the packets anywhere. You may think, hey, if this is a network thing and I need to route packets between somewhere, why the hell is there something called don't route? And that's only used if you are actually implementing a router yourself, which you may or may not, you probably don't use in your networking course, but if you need to implement a router or switch or something, that's when you would use don't route, when you really care about the path and you don't want to like go around infinitely because you are the router. So I guess that's it. So you perform networking through sockets. Everything's a system call. You can strace everything. If you don't believe me, I recommend you never believe me. You can just always strace things yourself if you really want. So strace Chrome, see what happens. But sockets are the actual IPC that just communicates across machines. Basics are sockets require an address, so like a local thing I used, which is just easier and local to your system, and then IPv6, IPv4, two types of sockets, stream and datagram. Sockets need to bind to address, listen, accept connections, have a whole bunch of steps for that, and then clients just need to connect to the address, and then you get a file descriptor with your two-way communication there. All right, we can use the rest of this time for fun, or ask me things about Lab 3, or study for your midterms, or do whatever. So just remember, pulling for you, we're on this together.